Right. So today I want to talk about information visualization. So you will notice two things. One, towards the beginning of the lecture, a repeat of some of the ideas that we have seen under visualization, but presented in a slightly different way. The second thing you will notice is that what we have covered so far under visualization focuses on techniques that were in close sync with the topics that we covered under graphics. But what we are going to see today, you will see there is a slight difference in the focus of just in the focus, whereas the entire pipeline is going to be the same. These are the two things that you will notice. So in order for us to get started on this topic of information visualization, I want to go back and revisit um, the introduction to visualization. But now I want to talk about it in the terms of the value that visualization brings. Right? So it's called the value of visualization. So after that quick introduction, where we distinguish between the topic for today and what we have covered so far under scientific visualization, I will then talk about visualization techniques, three different techniques. One is called tree map, one is called parallel coordinates, and then the other is called a scatter plot matrix, which brings together PCA, if you know about this, principal component analysis, and visualization. And then we'll end with some discussions. Feel free to stop and ask questions in between. So you may recall this slide where I talked about when I introduced visualization, I talked about visualization in our day-to-day life. For example, when if you are reading the news regularly, or where maps play an important role in bringing news from across the globe to you. Maps may be of different kinds. We have seen the difference between the two maps that you see here, the political map on the left, which preserves area and gives you a good sense of the size of different countries and continents, because that is that aspect um, uh, of the geography is important for the story, whereas the maps on the right is called a Mercator projection. This is used by sailors or navigators, and here the angle is preserved. So this is called a conformal map. And again, this conformal map is useful for navigators for their task, which namely navigating from one point in the ocean to another while traveling in straight lines. So charting the course, etc., on the map requires the map to be to satisfy this angle preserving property. Area is not much of concern in this context. So you already noticed that the data can be presented in multiple ways, depending on the need, depending on the task. So in this case, the data already has had a spatial context. So this is still scientific visualization, as we discussed in the past 7 to 10 lectures. Today, what we are going to do is to look at data that does not have a spatial context, or non-spatial data. So in this context, bringing that data into space, incorporating geometry is the most important aspect of visualization. And that is what we will focus on. So the resources, if you want to read more about this, so there are courses taught focusing only on information visualization, or in other words, visualization of data where there is no obvious spatial context. The book by Tamara Munzner is one of the most recent and comprehensive collection of concepts related to visualization. The introductory chapters in this book talk about the language used in visualization, and then it focuses on information visualization techniques. So it's a very good book, very easy to access for everyone. More importantly, Tamara does a great job of giving lectures about introducing visualization and making these lectures available. So there is, for example, if some of you attended the visualization conference last week, she gave a one-day tutorial on this topic within the conference. So those lectures are also available on her YouTube channel. So go and take a look if you are interested. At some point of time, I had also written an article, an introductory article to visualization. This is also something you could look at. If you have not seen this video by Hans Rosling that introduces statistics, descriptive statistics, or in other words, visualization, please do take a look. Hans Rosling is one of the champions of visualization. He champions the use of visualization to present your data in the best possible way. We will later talk about visualization systems. So those are also interesting resources, D3 and Tableau. So let's jump in and talk about the value of visualization. Let's start with a very simple task. So the task is this: you want to multiply two-digit numbers, right? So let's say 35 multiplied by 95. So these are pioneers in this domain: Stuart Card, Moran, and Ben Schneiderman. They ran this experiment on a collection of individuals. I think some of them were students, some of them were adults. So they asked them to run this multiplication in their head, and then do the same thing on paper. Of course, they give a different pair of two-digit numbers. And what they found was significant. If you see the chart on the right, the y-axis shows the time required to do the multiplication. So they found that using pen and paper or pencil and paper, right, reduced the time to do this multiplication significantly. Many people were able to definitely do the computation in their mind, but it took much more time. They ran this experiment in order to test one of their hypotheses, which is a visual aid helping us with our thinking capability, right? So what they found with this simple experiment is that, at least for this experiment, the visual aid helped people compute or finish their task 5 times faster. Right? There are multiple such experiments comparing the time required to do some task with a visual aid and without a visual aid, right? And the visual aids definitely help in our thinking process. So that's the way to think about visualization, that it is a tool that amplifies our cognition, right? That amplifies our understanding. Right? It's not a replacement for anything. It cannot be replaced by something that's automated. We always think of visualization as something that is amplifying our thinking capability, our understanding capability. Right? So another example here from the early days of mapping tools. So this is a line drawing tool developed by Manish Agrawala, who's from UC Berkeley. So this is from the early days of Google Maps. If some of you have seen screenshots of the very, very early days of Google Maps, so prior to that, there were a few tools that were available for planning your trip. right? So these there were several tools available in different one in every country, right? I think in India there was one tool which was popular called Map My India, if I recall. There were other similar tools in the US and Europe and so on. So these tools would often, what they would do is they will give you turn by turn instructions, like what you see on the right. So it will say begin in this avenue, turn right on this road, go for another so many feet or so many meters, and then turn left and so on. So these were good instructions, but you had to keep looking for example, the second instruction is turn right on Broadway, right? So you have to keep looking for this street called Broadway, and then you turn onto that. This was fine. It was very useful, right? And you could print this out. So I've done this many times. So you print these instructions and then you just go based on that, right? So this was prior to GPS becoming quite popular and available on the phone. But one of the important observations was that you don't need all this information, right? What you care about is uh, some kind of a mental map, right? So let's say you are going from home to work, right? And you do this every day, right, for many years. You have a mental map of the roads that you're going to follow, where you're going to turn, how you're going to turn, right? What is the angle at which you turn, and so on. So the idea of the line drawing tool was to get that mental map to you as early as possible, so that it sits in your brain, and then you are immediately able to use it to drive, right? So you know your home. So here the home is I think Ellsworth Avenue, and you know that this is the direction in which you go, and how you turn, and where is your destination with respect to your origin, right? So it gives you some context. It tells you some of the intersecting roads, but your focus is on the road that you are going to take, right? So, so this visualizing this path towards your goal already helps you do the driving, right? So in case even if you lose the GPS for some time, you have this mental map and you know how you're going, unless of course the instructions are too complicated, so you don't remember it anymore. So this is one more example from a century ago. Maybe I talked about this briefly during one of the discussions or a lecture. So this is about the cholera epidemic that hit London. So you know, so these were the days prior to um, antibiotics and um, uh, easy distribution of medicine and so on. So people didn't even have a sense of what an epidemic is. So cholera hit London in the mid 19th century. So the question was, what was causing it, right? What was causing all this sick people to go to the hospital? So here is the visual from one statistician, right? We'll see. So this is reproduced from a book by Edward Tufte, who is a well-known educator in this in visualization. So he showed this John Snow is a statistician who created a illustration of this epidemic. And I mean, the story goes that with this simple visualization, he could immediately say what is the reason for the epidemic, right? I'm not sure about that story, but the visual clearly helped him communicate his findings to the authorities and for them to take immediate action, right? So what did he do? He took all he did was he took a map of London, a street map. We'll see a zoom in version soon. And he plotted all, so this street map has all the streets named and so on, right? And it also had a few important things mapped. For example, the water pumps along the different streets right? So this is these were the pumps that supplied water to the individual houses. They were connected to wells and so on. So all he did was for every street, I think for every few blocks, he plotted the number of deaths that were local to that region, right? So the way he plotted that was similar to your bar chart as horizontal lines. So each horizontal line, let's say, corresponded to so many deaths, right? So he plotted multiple horizontal lines depending on the number of deaths per region. So you can see those bars here, right? So you could quickly see that there is this one close to this broad street where there is a huge spike of deaths, right? And they are high in certain regions, right? Um, so this allowed him to go and pinpoint some serious regions, right? And what they did was to go and test the water pump close to those high concentration regions. So what is shown here is a pump, the water pump next to that spike, and they found that was infected. They went and tested this at all the other spikes, and they found that the levels of infection was very high close to those water pumps next to the spikes. Now this also helped them go and fix the problem. They knew where to fix it first, right? And they could quickly bring the problem under control. So this is touted as one of the early applications of visualization to solve a health crisis problem. Okay, so I talked about Da Vinci quite a bit, who used visualization again to showcase different natural phenomena, right? So all that is similar, but in the sense that visualization helps you improve your understanding of what's happening. What was different with John Snow was there was no obvious spatial data. It was only collection of deaths, but he brought in the spatial context by locating the deaths and then mapping it to the locations of the water pumps, right? So in that sense, he helped improve the health authorities' understanding of the health crisis, right? So let's now talk, in this context, let's talk about visualization techniques. So we are going to now focus on data that does not have an obvious spatial context, right? So as examples, you can think about your mail logs. Who are you getting the mails from? Is it from school? Is it from your personal connections? Is it from like promotional emails? Is it from some subscriptions, right? So there is no spatial context here. This is just different kinds of emails. When do you get the emails? During the morning, during the afternoon, and so on, right? So that's one kind of data. Other census data, population data, right? So these don't have a spatial context. There are several techniques that one can employ to visualize such data. And these techniques are fairly common knowledge, so I don't have to even talk about them. So I've just listed many of them here for your reference, right? All kinds of charts, all kinds of scatter plots, and so on, right? Each technique has some advantage. You don't want to use a pie chart if you have to do some comparisons. You want to use a pie chart only if you want to talk about fractions. Otherwise, it doesn't make sense. So there are some do's and don'ts, but these are just common knowledge, right? So if you apply your mind a little bit to decide which technique to use, then you already have made a good choice, right? So that's the only thing I would say here. But I will take off from here to talk about one specific technique, that is tree map. Okay, but before, so let me jump in here again. Feel free to ask questions. So the tree map, this is a technique that you may or may not have seen. The tree map helps visualize hierarchy, especially hierarchy that can be stored in the form of a tree. This was introduced by Johnson and Ben Schneiderman in '91, and this year, in 2021, this original paper by Ben Schneiderman also received the Test of Time Award at the Visualization Conference last week. So it's a very timely topic for us. So the idea is very simple. You want to display a tree, right? It need not be a binary tree. It can be any k-array tree. But of course, we want to focus on a rooted tree. So there is some kind of a root. The tree stores a hierarchy. The idea is to use a 2D layout to display this hierarchy. And you want to use rectangles to represent the individual subtrees, the objects, and the nesting of the rectangles. So the indicates the levels of the hierarchy. The size of the rectangle tells you something about the size of the subtree and its comparison with the other objects. So let's look at an example to understand what this is. On the left is a tree. This comes from the original paper by Schneiderman. So what you have here is this is the root, right? So here you have the root. And you can see the hierarchy in the tree. Nothing to explain here. The root is represented by the rectangle that you see on the right, the entire rectangle. Now we notice that the root has 4 children. The first one is a leaf node with some number associated with it. So this is, you can think of it as the weight of a node in the tree. So this is a node with weight 12, and then the second node with weight 8, right? So that's B. There is a third node, C, and then the fourth node, D, right? The fourth node, C, has a total weight which is equal to the weight of all the descendants. So here, if I do a quick sum, this is 10, right? So this guy has a sum of 10, a weight 10, and whereas D has what is this? 25, 30, 70. Is that, hope that's correct, right? So it's a carefully chosen number, as you can see. If you notice, the root has 4 children and their weights are 12, 8, 10, and 70. So these weights are used to decompose or partition the rectangle into sub-rectangles. The first rectangle has weight 12. So the partition is along the x-axis, right? And so the first child gets weight 12. The next one gets 8, right? And then the third one gets 10. So the third one gets 10, as you can see, 10. And then the fourth one gets D, which gets 70. Right? So you can see how the rectangle is partitioned based on the weight of the children. So that's the idea essentially, right? So the first axis is based, this is partition with respect to the x-axis, right? And next what you do is the next level, you go down to the next level in the tree's hierarchy. And then you partition now with respect to y-axis. So so let me show that here. So the next level consists of nodes here, right? So they come in by partitioning with respect to the y-axis. So that is why you get these nodes 2, 2, 2, 3, and 1, right? So these are partitioned along the y-axis, and you keep swapping between x and y directions, and you get a nested hierarchy. What you see on the right is called the tree map representation of the tree on the left. That is the whole idea of a tree map. Hopefully that is clear. Now, this idea, one of the motivating applications was that when Schneiderman wanted to look at your file structure on your computer, right? In order to figure out what are the different types of files, which file is, which folder is taking up a lot of space, is there fragmentation, and so on, right? So they tried this idea, this vanilla idea, directly on their file structure, and this is the picture that they got. They used colors also to indicate different rectangles, to distinguish one rectangle from the adjacent one. I think there was some color coding also. Yellow, I think, is unknown. Green is for text. If you can read the thing here, green is for text, and then the cyan is for graphics kind of files. This is applications, the purple, and so on, right? From a first cut, this is not too helpful. You see these long, thin rectangles. You don't know who contains whom. This is not a useful visualization. The only few things that you can see is that, okay, there is this huge file called VM storage that takes up a lot of space, maybe, right? But it's quite possible that there is something else, some other file which takes similar space. We don't know whether it takes similar space or not, because you may have a long, thin rectangle, right, whose area may be similar to something like this, right? Now, it's very difficult for a human to compare the areas of these two guys, right, to tell which is bigger, which one is bigger and which one is smaller. So this initial idea was helpful to identify a few outliers. Yes, it was possibly useful to identify the hierarchy, but it was not clearly useful to compare sizes of objects. So this was 91. There were a long list of papers after that, which helped solve these issues. So some of the issues, like I said, is with the tree map, that it's disorderly. So the adjacency is difficult to understand. The aspect ratios change significantly, that lead to skinny rectangles. And these rectangles are difficult to compare. They also clutter up your image, making it difficult to read. Overall, your understanding is made difficult because you cannot clearly look at the nesting, the hierarchy. The color, it's not clear if color helps you at all, right? In this particular case, the only reason to put in color was to distinguish different types of files. So maybe this is just the wrong application of tree map. Maybe you don't need a tree map to show your file structure in the operating system. Or you need to modify the tree map, right? So there were a lot of attempts to improve this representation, as is true in any research endeavor. So the first attempt may or may not always click. So the future attempts were based on a more careful analysis of the application of tree maps. You typically want to break your tree into meaningful subtrees, and you want to highlight them, right? So you want some kind of meaningful groups. you want the appearance to be usable in the sense that you should be able to compare the size of objects, which means that it will be good if many of them have similar, if not the same aspect ratio. Um, if you have a very deep hierarchy, then again it becomes difficult to understand nesting. Um, Color makes sense only if there is a specific task where you want to use the color. Maybe you want to use just two colors to distinguish who is beside whom. Um, so there were several such observations. One more observation was that there was no interaction in the initial version of the tree map. So interaction may have helped, right? It may have helped by giving you access to the actual data corresponding to every rectangle. So there were several such considerations that led to developments. So something that is used nowadays is a variant of what you see on the bottom right. So this improves from the figure that you see from the top, where you have these thin, skinny rectangles and so on. There were developments one at a time that led to something called cushion tree maps. As you can see, there is no color here. Color can be added to additionally incorporate other information. So you will immediately notice that the tree is that there are different boxes, and their boundaries are clearly demarcated. Right, so you can clearly see these boundaries, and you see that this red box is lying within another larger box, which is also nicely visible. And so this visibility is enhanced by using shading, uh, by shading the boundary and then increasing the specular reflection towards the center. So that's why the term cushion tree maps. So you can look this up. You can just look for the reference. I think it's there in one of the slides also. This appeared in 1999, if I recall. So this shows the different important subtrees. You notice that the aspect ratios are also more or less square. So these are squarified tree maps. And the hierarchy is not too deep. And some of these tree maps also support interaction. So the issues that we raised earlier have been addressed in subsequent works. Right. So like I said, this is the reference from 99. If you want, you can go and look at this technique in more detail. So this version or variants of this tree map have since then been successfully used for several applications. Many people have worked on this and have brought it to kind of more popular use. So you will see tree maps a lot in certain application domains now. For example, in the stock market, I think this is used heavily, thanks to one of the early introduction. I think the original website is no longer available. I think the original one was something called Smart Money. So this was done by one of a visualization researcher called Wattenberg. But I think his webpage lists this if you want to take a look. So the focus here is interaction. So this is about stock prices. You know that the stock market distinguishes different types of companies. So they distinguish them here explicitly. So here, if you read carefully, this is called the energy sector, this is the transport sector, and so on, right? So that's clearly something that an investor would be interested in. The green indicates upward trend, and the red indicates downward trend. So you clearly can see which prices are increasing, which ones are decreasing. The intensity tells you how much they are increasing. So you get a lot of information just from the first view of this tree map. So you get to see the different sectors, how are they with respect to each other. So you can quickly see technology is much, much bigger than the others. Um, uh, and it's green more or less overall. You see which sector is not doing too well during that time. In this, I think at this time, transport was not doing too well. And there is interaction. So if you click on technology, this will give you the sub categories within technology in a zoomed in view, right? So, so that interaction helped you work with the tree map. There is a similar application to coffee selection. If you want, you can take a look at this also. So there's several applications of tree maps. This has become more mainstream now. The second thing I want to talk about is high dimensional data. So again, when you have data in higher dimensions, there is no obvious spatial context. So you need to bring in the data into space so that you can visualize it. Let's first define what high dimensional data is. If you have what we have seen so far is scalar fields, right? Where you had f and the domain of the function was Euclidean space, for example. But now let's look at f that goes from some domain, right, to some range, right? So let's say that the domain is some space in higher dimensions, which where every point can be specified using n coordinates. So this is a n-dimensional space, right? So any point has n coordinates. In this point, f maps this point to a point in the range, which is, I mean, it can be a scalar, in which case there's only one value, or it can be an m-dimensional space, right? Need not be Rm, Rn, Rm. It can be any n-dimensional, m-dimensional space. So we call the data n-dimensional based on the domain, right? And we call this data to be m-variate because there are m right. So this is some. So if m is 1, then it's a univariate. Otherwise, it's multivariate, right? So far, we have looked at scalar data and maybe a little bit at vector data. So in general, it can be m-variate data. So for now, let's just look at high dimensional data, n-dimensional data. Not worry too much about the variate property, right? So if you have two-dimensional data, we know how to display it. For example, if they are scalars. So you have the two coordinates here, x1, x2. The way you show the two coordinates is with respect to the axes. And you present the axes as orthogonal axes, right? Each point in the domain is a point in this plane. And so you can display the collection of points from the domain. At least that is easy. And if you want to map that to some value here, maybe you can show that using color or whatever. We could do this up to 3 dimensions by still drawing things on the plane. Even though with 3D we use some kind of projection, right? But here, even if you notice here, the axes are displayed as orthogonal to each other, right? So this follows from linear algebra, really, right? We think of the representation as in terms of a basis, and hence we want to think about x1, x2, x3 as orthogonal to each other, and then that's why the representation is natural. Now, when you go to multidimensional data, one practical difficulty is you cannot draw more axes on the plane and still keep it orthogonal to each other, right? So this is a problem. So visualizing high dimensional data becomes very difficult because there is not enough space on your paper or on the plane. How do you address that? Okay, so that's the question. So one solution is parallel coordinates. The idea is, instead of thinking of instead of drawing the axes as orthogonal to each other on the plane, you draw them parallel to each other, right? So here there are this is 4-dimensional data, and each axis is shown as a vertical line. So the first axis is maximum sepal width. The next one is maximum sepal length. This is the third. So you can think of this as your 4 x2, x3, and x4. Right? So the 4 axes are drawn parallel to each other. So this is just a visual representation. So if you have a point now, x1, x2, x3, x4, right? So this would be a point in that 4-dimensional space, but in this parallel coordinate representation, this will be a polyline. So this is x1, this is x2, this is x3, and this is x4, right? So the point that I'm drawing is corresponds to a polyline here, right? Hopefully that makes sense. So in parallel coordinates, every data point appears as a polyline, right? Now, there are many properties that naturally follow due to this representation. But I'll go through them one slide at a time. But before that, let's quickly see one of the benefits of this parallel coordinates. I can so now, instead of looking at points, I need to look at polylines and how they collect together, right? So for example, you notice that if I choose all these polylines that begin with capital X4 in this range, right? You will get a collection of polylines. So this is what has been done here for the green, right? So I think the selection is made from here, from the maximum petal width. So this portion is selected and tagged green, and all the polylines that pass through this interval have been colored green. So this tells you, so this is essentially the same as selecting a bunch of points in your scatter plot, right? So you can do similar selections in the parallel coordinates view. This allows you to understand how the points are distributed. So you can see, for example, here that there is some relationship between x3 and x4 because selecting a contiguous set of values for x3 gave you more or less a contiguous set of values for x4 as well, whereas x2 and x1 is diverse, right? So you could similarly select something here for x4. So together with interaction, this parallel coordinates helps you understand your high dimensional data. There are a few things to understand before using parallel coordinates. So for example, ParaView supports parallel coordinates. If you have high dimensional data, you can just generate the parallel coordinates view and try to interpret it. A few things that you want to note. If you have two coordinates, so you have 2-dimensional data, so let's say you use a scatter plot. On the top row, you see some interesting patterns. that are familiar to you. Positive correlation on the right, negative correlation here, and no correlation, right? Corresponding to the R equal to 1, 0, and -1, the correlation coefficient. In parallel coordinates, the corresponding patterns that you need to watch out for are for R equal to 1, the positive correlation, you will see a collection of parallel lines. You can imagine why this is true. For R equal to -1, you will see a bunch of lines that cross top to bottom, and in the ideal case, they will all pass through one point in the center. And R equal to 0, you see really a mess, right? Some lines going horizontal and some lines going upwards and others going downwards. It's not so easy to figure out R equal to 0, right? But R equal to -1 and 1, or R equal to high value, is easier to identify. So why is this true? This is because of the duality property between lines and points. What we have done is taken a point here, since the axis is x1, x2. So one point in the primal space, when you represent it in the parallel coordinates, this appears as a polyline, right? Or as a line here, because it's just two coordinates, the orange line. So what this means is, well, this is exactly the same, right? So the x1, x2 here, the point is the same as the orange line. If you think of A as the primal space, then B is your dual space, and you can work with them interchangeably. There is a nice duality between points in the primal space and lines or line segments in the dual space. So this duality can be taken forward if you have collinear points. So for example, green, blue, the green line, the green point, the blue point, and the orange are collinear. This corresponds to line segments that pass through a common point, right? And there are similar such duality properties that you can think about, right, when you extend this to polylines. So the patterns that you see in the scatter plot will have corresponding patterns in the parallel coordinates view. Once you're able to recognize them, it becomes easy. One benefit of the parallel coordinates is that you can extend to as many axes as you want, because there's a lot of space on the plane to draw parallel axes. With parallel coordinates, you can also show hierarchy using colors. For example, what is shown here is color via proximity. So there are a lot of data points here. A few of the data points. So there is already some clustering that's done, and the cluster representatives are shown in solid. As you can see, I'll just maybe indicate one of them. As you can see here, right? So this is one of the cluster centers, and proximity to this cluster center is represented via a blended color. So you can see for 5 different colors for the 5 different clusters. So this is one way of visualizing different clusters, and you can of course do the clustering hierarchically and still represent the subclusters and so on. There are many other additional variants of parallel coordinates that help further study your high dimensional data. Okay, so by the way, if you're curious, you may have heard the name of this data set. This is called the IISc data set. This comes from the study of plants, or actually flowers. This is the UC Irvine one of the classic data sets. It's now more or less a toy data set because we have much bigger ones. This is in the early days, this was used for ML as a benchmark. It has many features. I think 4 is what we see here. Okay. Parallel coordinates is not without challenges, not without problems, right? It's not something that solves all the issues that you have with orthogonal axes. Here are some issues. The axes don't have an order, but you are enforcing some order left to right. This can have side effects, so you have to be mindful of this. One way to address this is to allow for the user to swap the axes or to find some optimal ordering of axes. Martin Inselberg in 1999 came up with this idea of parallel coordinates, and soon within a few years he wrote a book that describes this entire idea together with the different variants. One approach that he proposes is to use some kind of a learning approach to even identify the axes orders. So he has built different visual analytic systems using parallel coordinates and has shown that they have been shown their use to solve many different problems. So he has a book. I forget the exact title, but something to do some parallel coordinates and interactive study, something similar to that. So if you are interested, you can take a look at Inselberg's book on parallel coordinates. The third technique that I want to talk about quickly before we wrap up today is the scatter plot matrix. We all understand scatter plots. If you don't, the idea is quite simple. You have a bunch of data points. Let's say you have the axis is xy. You have a bunch of data points x1, y1, x2, y2, and so on. You display each one as a point in 2D space, and this collection of points is a good representation of your data. This is called a scatter plot. If you have high dimensional data, you can imagine a scatter plot matrix where on the x-axis you have the different axes. So what we earlier called x1, x2, x3, x4, and so on. And the same on the vertical axis, right? So this forms a matrix. Every entry in the matrix corresponds to one pair. So this corresponds to x3, x1, right? So for this entry, you draw the scatter plot for that particular pair, x3, x1, right? So clearly, this is a symmetric matrix. The diagonal entries are not really meaningful because they just show the scatter plot for x1 with x1 and so on, which will always be the main diagonal. So often what people do is that instead of showing the scatter plot along the diagonal, they show something else, some kind of a autocorrelation or for example, some other statistic on that particular variable along the main diagonal, right? So there are variants that show something different along the diagonal. This matrix is also symmetric, which means that the entry here shows x2, x1, which is the same as the x1, x2 entry. So there is no need to show redundant information. So oftentimes this visualization is modified to show something different. For example, the correlation coefficient together with some other statistics in the upper triangular part of the matrix, whereas the lower triangular part shows the scatter plot. There are variants such as this. So the scatter plot matrix is another very useful visualization technique for high dimensional data. This is also supported in many visualization tools. Of course, as the number of dimensions increase, the matrix also becomes large in size. So you could identify important variables, maybe by doing some prior analysis, and then use them to populate your scatterplot matrix. This will avoid clutter and give you a neat visualization. So to summarize, I talked about very briefly, we didn't jump into details at all. Very briefly, we talked about the tree maps, parallel coordinates, and scatterplot matrix as three different techniques for high dimensional data visualization. So these are just examples of information visualization techniques. I want to just end with giving you references to some visualization systems. Some of you are going to present this in the coming weeks. So these tools that I'm going to talk about here are primarily focusing on information visualization. The IISc tools are also part of our list of presentations. D3 is a JavaScript-based library toolkit for visualization on the browser. Very popular, very wide community that supports this. Almost all the visualizations you see from newspapers, particularly nowadays with showing COVID-related data, they were all written using D3. So incidentally, D3 also received the Test of Time award in the previous in the last week's visualization conference. It's been 10 years since D3. Tableau is one of the leader in visualization software. I think they've been bought over by Salesforce now. They have academic licenses available. They also have free copies for students. So you can download and look at this. This is an interesting combination of databases coming together with visualization. So D3 was developed in the University of Washington, and the same group has developed several other tools. One important tool is Vega and Vega Lite. This brings together automated visualization tool ideas. So if you're interested, you can look at that also. There are a lot of interesting projects that are happening in different companies and in the public domain. Google has a Google AI team called Google Brain, and one of the main divisions there is AI and explainable AI and bringing visualization together with that. So if you're interested, you can look at this set of works that they have done here under this link. One of the developers of D3, Michael, I think, Michael Bostock, has started another project called Observable HQ. So this brings together different code blocks. I think the whole project was called blocks earlier. This allows you to take your visualization to the web and to the wider world. So do take a look at them. There are several interesting visualizations that have been created there. This could serve as inspiration for you for now, for your project, or for later. Right. So I will end there. There are a few more things but this is more self-reading. There are some charts here that I want you to critique and find out interesting things that are good or bad with this visualization. So I will stop there, and if there are questions now, I can take them. Maybe initially I'll focus on questions related to the lecture. Any questions?
Hello, sir.
Yeah.
Yes, sir. So one question is, so I have been using this information visualization right from our undergraduate for a lot of data processing things. But the one thing that I always have a problem is like, how do I decide on what is the best visualization tool for my data? There can be multiple data tools for a same set of data which can represent that data well, but how do I decide the best? That is one thing that I always had doubt. How about to decide that, sir?
Okay, so there are two answers to this. The first answer is a little bit subjective, but that's more prevalent. So I'll give that first. It comes with experience. So as you develop more visualizations, as you look at more data sets, you you see the benefit of the visualization in hindsight, and you see how good it was, how useful it was to answer your questions. And based on that, you develop your own set of favorite visual representations. That's subjective. There is an objective answer also, but this is a course in itself. So the book by Tamara Munzner does this in a very methodical way. So the way she introduces this is by talking about first the types of data that you are working with. So when you're working with the data, you first want to recognize what is that kind of data you are working with. So you have to do that classification. Next, you want to go and classify what kind of tasks you want to accomplish using this. So then you write down those tasks and what are the classes that they belong to. Now, she talks about an important chapter there is something called marks and channels. So these are visual encodings of your data. As a simple example, um, if you want to display height information for everyone in a particular class, the channel the visual encoding channel you use often is length corresponding to the height. So you use a bar chart where the length of the bar indicates the height of that particular student, right? So she talks about the different channels, and there are a lot of studies that tell you which channel is better. Is it the length channel, the position channel, the area channel, and so on, right? So once you learn this terminology, so these are the three things, starting with data type, the kind of task, and the visual encoding, marks and channels. Once you understand this, you have the necessary language to say whether your encoding is good or is appropriate or not. Okay. Uh, Again, this even after doing all this, there is some experience that will come in. Right? But these introductory chapters from Tamara's book would be a good starting point, I would say. Right? But a lot of those chapters are uh, easy enough for self-reading. So I would encourage everyone to just go and read it.
Yes, sir.
Okay. Any other questions? So like I mentioned, today's topic was focusing on techniques where there was no spatial context. And in that, I talked about primarily high dimensional data. Now, I think in one of the future lectures, I think I will talk about tree and graph data specifically, and talk about visualization techniques for those networks and graphs, and of the special case, which is trees. Right. So I will, at that time again, there will be no obvious spatial context. So we have to come up with a new spatial embedding. So these will be the two lectures in the broad topic of information visualization.